Hi everyone, and welcome to my talk on sign patterns and their applications. This work was made possible by an NSERC Undergraduate Student Research Award under the supervision of Dr. Kevin Vander Meulen and Dr. Adam Van Tuyl. Suppose that we have two rooms, and in each of those rooms there is a crowd of introverts. What we know about introverts is that they don't like crowds. Introverts will try to move away from the crowd to try to find a more sparse room, a less crowded room. So the more people there are in a room, the faster the introverts are going to leave that room. We can describe a system like this with these equations, where x1 is the number of introverts in room 1, or the density of introverts if you like, and x2 is the number of introverts in room 2. dx1 by dt is the rate of change of introverts in room 1, and dx2 by dt is the rate of change of introverts in room 2. And in this case, we're assuming that a quarter of the introverts from each room will move to the other room in a unit of time. We can describe this using a system of vector equations. So we can have x as the vector of x1 and x2, and dx by dt is the vector dx1 by dt, dx2 by dt. So that describes the rate of change. And we can set them equal to each other if we multiply by this matrix A, where you can see the matrix A below is just the constants in this system. The useful thing about being able to do this is that we can solve the system much more easily by isolating this matrix A. If we find the eigenvalues of A, we can solve this system. What's an eigenvalue? Well, technically, what an eigenvalue is a number such that there exists a vector, where multiplying that vector by that number is the same as multiplying that vector by the matrix. In general, every matrix has certain vectors and numbers so that this is possible. And in this case, we don't really care about what the technical definition of an eigenvalue is. What we really care about is that an eigenvalue is inherent to the matrix. You can't have the same matrix with different eigenvalues. Another interesting point is that the matrices that we're considering have only real entries. So an entry in the matrix could be 0, it could be 1, it could be -1, it could be -1/4. It could also be pi, but that's sort of the range we're looking at. Whereas when you have even a real valued matrix, it can have eigenvalues that are complex. So complex eigenvalues have a component of the square root of -1. So for example, 1 plus I, or 1 plus the square root of -1, is a complex number. And this will become relevant later. So back to our specific matrix, it has eigenvalues 0 and -1/2. So in general, the solution is going to look like this, where C1 and C2 are constants. In this case, C1 should be multiplied by e to the power of 0t, but e to the power of 0 is 1, and anything times 1 is just itself. So we can write it more cleanly like this. And if we graph these two solutions, plugging in C1 and C2 based on some initial conditions, we get this graph. Now, I've deliberately excluded the axes because we don't actually need them. So the point I'm making here is, first of all, that in this system, you start off with a different number of introverts in both rooms, and then as time goes on, introverts move so that it converges, so both rooms end up having the same number of introverts in them. The second point I want to make is that this would happen regardless of how fast the introverts are moving. So in this case, we assumed that a quarter of them move from one room to the other in a unit of time. But we could have assumed that number was a half, or that number was a tenth. Either way, we'd get the same result. It would just happen at different rates, right? It might happen more quickly or more slowly, but we're still going to ultimately end up with the situation where we have the same number of introverts in each room. Somehow, we just needed to know how they were moving and not necessarily how fast. And in some sense, all that really mattered was the sign pattern of our matrix. I'm neglecting a few factors here, but the sign pattern is still a very useful and very informative tool in this case. A sign pattern, formally, is an array with entries from 0, minus, and plus. And generally, we're concerned just with square sign patterns. So what do I mean by that? Well, if you take a real matrix, like for example the matrix that we had before, and you take each entry there that's negative and you replace it with a minus sign, and each entry that's positive and you replace it with a plus sign, then you end up with the sign pattern of that matrix. And so many different matrices can have the same sign pattern. And in some linear systems in the real world, we don't really know the exact values that go into a matrix that describes that system, but we do know the sign pattern of that system. So this is where the study of sign patterns can be useful. The study of sign patterns originated in economics, but it has since been applied to many other fields, like physics, and it has found a lot of biological applications. So, for example, you can consider a predator-prey model, where we have some species of plant in two different forests. We have an herbivore that can move between those forests, and we have a carnivore that can eat the herbivore and can also move between those two forests. And by describing the rates at which each animal can eat its food and the rates at which they can move between the two forests, we can actually turn that into a linear system and solve it with what we know about sign patterns. Or at least find out what the solution ought to look like. The focus of my research has been to look at sign patterns and see how much can we tell about a matrix, about the eigenvalues of that matrix, based only on the sign pattern of that matrix. So this is a little bit of jargon, but in general, when you have a matrix with eigenvalues lambda 1, lambda 2, up to lambda n, it has n eigenvalues, it has a general solution that looks like this, where you have all these c's are constants, just numbers, and all the v's are vectors. So you can think of them as a direction in n-dimensional space. And so you can see what's going on is that we're just adding together these different terms that are all e to the power of an eigenvalue times t. And each one of those terms is sort of going in a different direction, so they're not going to cancel out. So what this means is that we're adding a bunch of exponential functions together, and we understand how exponential functions work. If you have e to the power of t, so e to the power of a positive number times t, then it's going to start very small, and then as t gets bigger and bigger, this function is going to get bigger and bigger and ultimately blow up. If we have e to the power of negative t, or e to some negative number times t, then we're going to start very big, but as t gets bigger and bigger, it's going to get smaller and smaller and ultimately converge. And if we have e to the power of 0t, then it's just going to flatline. It's just going to be a constant. So this solution is only going to converge if all of the eigenvalues, all of the exponents, are negative. Why all of them? Well, consider if you have some of them negative and some of them positive, then it'll converge in some directions, but it'll blow up in some other direction. So in that respect, it's not really converging. So this is where we get the definition of stability. So we say a matrix is stable if all of its eigenvalues have negative real part. Now, as I said, there's also an imaginary part, so eigenvalues can be complex. And here we have a complex grid, or a complex plane. You can see that we have the real part of the eigenvalue on the horizontal axis, and we have the imaginary part of the eigenvalue on the vertical axis. And what really matters is not so much where the eigenvalue is up or down, it matters where it is relative to that imaginary axis in the middle. So you can see if a matrix had these 6 eigenvalues, then it would not be a stable matrix, because although it has most of its eigenvalues with negative real part, most of its eigenvalues are left of the imaginary axis, it has these 2 positive eigenvalues at 2 and 3. So for that reason, it's going to blow up in some direction. Okay, so we've been sort of skirting around this imaginary component, and it's time we face it head on. So how do we make sense of an eigenvalue that is complex and has an imaginary component, right? I mean, we can't measure that. We can't measure an imaginary component in real life, can we? So the way we deal with this is using something called Euler's formula. And you can see Euler's formula here. I'm not going to go through the whole derivation, but the ultimate result that you should be interested in is that we end up with e to the power of a constant times t times some sines and cosines, where that constant, it's e to the power of the real part of the eigenvalue times some sines and cosines. So what does that look like graphically? It looks kind of like this. So the sines and cosines are going to contribute an oscillation. The imaginary component, therefore, contributes an oscillation to the solution. And that oscillation is multiplied by an exponential function that has the real part of the eigenvalue in it. So you can see if the real part of the eigenvalue is negative, we're going to start off with some very big oscillations, but as t gets bigger and bigger, we're going to converge as the oscillations get smaller and smaller. If the real part is 0, then we have these constant oscillations that never get bigger or smaller. So they're not converging, but they're not blowing up either. And then, of course, if we have a positive real component, then it's going to start very small, but the oscillations get bigger and bigger and bigger until eventually they just blow up in size. So again, we need the real part of the eigenvalue to be negative. We don't so much care about what the imaginary part of the eigenvalue is. I'd also like you to note that sign patterns don't tell us everything. So just because you have a certain sign pattern doesn't mean that you have a certain number of positive and a certain number of negative eigenvalues. Things can move around. So here's an example of a sign pattern. And in this sign pattern, I'm changing one entry just by a little bit. And you can see that as I change this top left entry by just a little bit, if I subtract just a little bit, then I move the eigenvalues to the left of the imaginary axis. And if I add just a little bit, then I move the eigenvalues to the right of the imaginary axis. So in this case, the sign pattern doesn't exactly tell us where the eigenvalues are. In some cases they do, but in this case it doesn't. This process by which I can move the eigenvalues either to the left or to the right of the imaginary axis is called a Hopf bifurcation. It needs a name, so it's called a Hopf bifurcation. It's a critical point where I could move these eigenvalues either to the left or to the right, and that makes a difference as to whether or not the solution is stable. Okay, and then the last sort of piece that I needed to use in my work is this idea of a signed digraph. Digraph stands for directed graph. So why are these important? What are they? It's basically a bunch of points called vertices, and they're connected by arrows called edges. And the idea is that the arrow is directional, so just because you're going from 1 to 2, you're not necessarily going from 2 to 1. So this is an example of a signed digraph, and its construction works like this. I look through my matrix, and wherever I see a minus, I'm going to draw a red arrow from the vertex with that row's number to the vertex with that column's number. So, for example, if we look at vertex 1, the first row and the second column, there's a negative sign. So we draw a red arrow from 1 to 2. In the first row, third column, we have a plus sign. So we draw a blue arrow from 1 to 3. In the fourth row, first column, we have a negative sign. So we draw a red arrow from 4 to 1. And so on and so forth. And this is how we construct this signed digraph. It turns out that a signed digraph can actually tell us a lot about our sign pattern. And in fact, all we really need to know about the signed digraph is where there are cycles and how those cycles are touching. So what do I mean by cycles? A cycle is just a place in the digraph where you can go around, start at a point and then end up at that same point without having to touch a point on the way more than once. And the cycle has a sign that's equal to the product of all of the edges. So for example, if you look at the positive 3 cycle on the left here, You can see if I start at 1, I take a negative edge to 2, a positive edge to 4, and then a negative edge to 1. So I have negative times positive times negative. The two negatives cancel out, so it's a positive 3 cycle. So it turns out, if all I know is where there are cycles and how those cycles are touching, and what the signs of those cycles are, then I know everything I need to know about the sign pattern without having to know what each of the entries is. So now some results. Here, we'll start with some results that were found before I started this project. So Bodine et al. In 2012 showed that if I change the numbering of the vertices, then it doesn't change the eigenvalues of the corresponding matrix. So this might seem sort of obvious that, you know, the graph looks exactly the same no matter how you number it. It's just, you know, you move around some labels. But it's less obvious when it comes to a matrix, because if you switch around rows and columns in such a way that you end up with the same graph but different labels, then you're going to end up with a very different looking sign pattern. So Bodine et al. Says that if that sign pattern still produces the same signed digraph, then it's equivalent. It's going to have the same eigenvalues. Another result from Bodine et al. Was that if your matrix has a digraph that looks kind of like this, so there's sort of two clusters, each of them is like a digraph in itself, and the clusters are only connected in one direction, so you can see the arrows are only pointing from the cluster on the right to the cluster on the left, then we can actually pretend that these are just two separate clusters that are completely unconnected in two different matrices, and we can just take the eigenvalues from one and the eigenvalues from the other, and those will be the eigenvalues of our matrix. So why is this the case? So remember I said that all that was really important is cycles. All that was really important is whether you're able to start from a point and then go through a bunch of edges and come back to that point. Well, if the arrows are only connecting these clusters in one direction, they can never be part of a cycle, because I can never come back to where they came from. So for that reason, we can actually treat this as two separate graphs. Okay, now let's get into some things that I was able to prove over this summer. So the first theorem I'd like to talk about is this one. So if we have a sign pattern that allows all of its eigenvalues to be negative in one case, if I choose certain values, and it allows all of its eigenvalues to be positive in some other case, then the digraph of that sign pattern must have a positive one cycle and a negative one cycle. So this is the example that we had before, and you can see that it has a positive one cycle and a negative one cycle, so maybe it can allow all of its eigenvalues to be negative, and it can also allow all of its eigenvalues to be positive. Again, it depends what values you choose for the entries in your sign pattern, but a sign pattern that has this digraph will allow some cases where all of the eigenvalues are negative and all of the eigenvalues, in some other cases where all of the eigenvalues are positive. The next one is a little bit of a mouthful, but sort of elegant to see. So suppose you have a path sign pattern. What does that mean? It just means you have a whole bunch of vertices and they're just connected in a line by 2 cycles. There are no 3 cycles or 4 cycles or anything like that. If you have a number of points that's divisible by 4, and there's at most one cycle on the way, could be anywhere on any of the vertices, but there's at most one of them, and only the first 2 cycle is negative, then any matrix that has that sign pattern has at least one positive real eigenvalue and at least one negative real eigenvalue. So I know about these eigenvalues, both that one of them is positive and one of them is negative, and that both of them are real. They don't have an imaginary component. At least these 2 eigenvalues. So that's sort of a mouthful, but it's still an interesting result. The last thing I'd like to mention is a conjecture that we have. So this is not a result because we haven't been able to prove it. We have tried to sort of run experiments and see if we can disprove it or see if we can find more evidence to support it. And so far everything is consistent, but we haven't been able to generate a proof. The conjecture is that if a sign pattern allows stable matrices and matrices with a number of Hopf bifurcations, then the signed digraph of that sign pattern must contain a -2 cycle. And we're pretty confident that this is true just based on what we've seen so far, and we know in certain special cases it must be true, but we don't know if this is true in general yet, so right now it's still a conjecture. Thank you. I hope you enjoyed.